Section 1.2 is called Functions and Graphs. And the first topic we're going to cover in this section is something called function notation. Hopefully you're familiar with this equation from what we just did, section 1.1. It's just the equation of a line. And if I want to rewrite that in function notation, it would look something like this. Note, I've just replaced the y with this notation, which we call f of x. The f is the name of the function, and that name can vary. We'll have different letters here. And the x is the input to the function. So basically what this means is whatever is in these parentheses, I'm going to put in place of this x. And the reason we do this is because it makes it easier to put different inputs in. For instance, f of 5 just means take our original equation and where we see the x, put in the number 5. And then simplify to get the final answer of 11. And you don't always have to have numbers. For instance, I could plug x plus 1 in for x. And I do exactly the same thing. I take my original equation and I put x plus 1 in place of the x. And you'll note that everything I'm putting in, I put in parentheses. And it wasn't really necessary up here because it's pretty obvious we're doing 2 times 5. But here it is necessary because those parentheses help us to remember that I need to distribute the 2 over both of those elements that I've put in place of x. So I have to do 2 times x and then 2 times 2. And the 1 just comes down. And then I can simplify. And we don't even have to have any numbers at all. I can just put in strictly variables. And we'll do exactly the same thing. We're just taking whatever's in here and putting it in place of this x. Again, we want to keep them in parentheses so that we remember to distribute that 2. The next topic we're going to discuss are relations and functions. And a relation is just any rule that takes elements of one set, which we call the domain, and assigns them to elements of another set, which we call the range. For instance, my rule might state that A goes to both 1 and 2, B goes to 3, C goes absolutely nowhere, D goes to 2, and E goes to 5. And that's a perfectly good relation. And usually you'll see these written as ordered pairs. And in ordered pairs, the domain element comes first, and the range element comes second. So if I were to write this as an ordered pair, I would have A going to 1, A also going to 2, B going to 3, C's going nowhere, so I'm not going to put it down, D is going to 2, and E is going to 5. So these are the same thing, just written differently. Now if I were to ask you for the domain and range of the function, just make a list of all the first elements. the A, the B, the D, and the E. And if they repeat, we are just going to omit the repeats. So the domain of this function is A, B, D, and E. Range is pretty much the same thing, except instead of the first elements, we're looking at the second elements. So the range is going to be 1, 2, 3, and 5. Because the 2 repeats, I'm not going to put it down twice. I'm only going to put it down once. So we've worked with our first relation, and we found its domain and range. Functions are relations, but they're a special type of relation in which each domain element can only go to one range element. For instance, this one is not a function because the A is going to both 1 and 2. Usually, on exams and in homework, you're going to get the relation or the function given to you like this. And they're going to ask, is this a function or not? The trick here is to look at the first elements, and if any repeat and go to different range elements, then it is not a function. So here's the problem of a type you'll see on the exam. And what I want is the domain and the range, and I want you to tell me whether it's a function or not. So for the domain, we just take a list of the first elements and try to put them in order, but if some are out of order, it really doesn't matter. And the same with the range, except we're making a list of the second elements. And again, if they get out of order, that's okay. So here is the domain and range of this relation. Now the question is it a function or not? And if we look, the 2 is repeated, and the 2's are going to different elements. Here the 2's going to the 1, and here the 2's going to a 6. So this is not a function. And the 2 points that prove that are the 2, 1 and the 2, 6. The next type of problem you're going to get is to determine the domain and range from the graph. What you need to remember here is that domain represents the x's, and the range represents the y's. And for the x's, you're going from smallest to greatest, or from left to right. And for the range, you're also going from smallest to greatest, but that means going from bottom to top. So let's check out the domain first. And for the domain, think of an imaginary line moving closer and closer to your figure until it hits the left-hand side and can't go any further. And what you'll see here is it hits at the point -2. Now there's an open circle at -2, which means we're not including that point. So in interval notation, not including the point is represented by an open bracket. And that happens at the point -2. Then, for the other point out here, take our imaginary line and move it closer and closer to our figure until it hits the figure. And then we want to see what x-coordinate that happened at. And that happened at the x-coordinate 3. Now there's a closed circle here, and in interval notation, since we're including the point, that's represented by a closed bracket. So the domain of my figure is -2 with an open bracket to 3 with a closed bracket. And we're going to do the same thing for the range. I'm going to start down here, and I'm going to move my imaginary line closer and closer to the figure until I hit it. And then I'm going to ask what y value that happens at. Well, that happens to occur at the y value, -2, and that's a closed circle. So I get a closed bracket and -2. And then for the upper bound, I'm going to bring my imaginary line down until I hit my figure. And that's going to happen at the y value of 1. But remember, that's an open circle, so I have to represent it with an open bracket. Now let's try the same thing with a parabola with a vertex at 2, 1 opening downward. We'll start with the domain. And remember, the domain is the x values going left to right. So I bring my imaginary line in, but remember what that little arrow means. It means that it's going out forever in that direction. So no matter where I put my little line, this graph is going to touch it. So basically, the x values go out this way forever, which means -infinity. And infinities, positive or negative, always get an open bracket. And now let's do the same thing on the right. And we have the same thing. Because of that arrow, no matter where I put my line, I'm going to hit that graph. So the graph goes to the right forever. So my domain is going to be -infinity to infinity. Now let's try the range. In range, remember, we go from bottom to top, and as I bring my invisible line up, I still have those arrows, so that means the graph goes down forever. So the range goes down to -infinity, and for the top, as I bring my line down, I stop right there. And the y value of that is 1. And since it's a closed dot, I get a closed bracket.
Now let's try a difficult one. Okay, looking at the domain of this, as I go from left to right, I'm going to hit the figure here at an x value of -2. And because it's a closed circle, it's going to get a closed bracket. Now the problem here is there's a gap in here. I can't just come from the right-hand side and figure out where it intersects this figure. I need to just keep moving my line along. So I have a graph at -2, and I keep intersecting the figure until this point right here at 0. And it's a closed circle. So I'm contacting my graph between -2 and 0. And they're both closed circles, so they both get closed brackets. But now I have another part of my graph. So I keep going until I hit the graph again. And I'm hitting the graph at 2. Open circle, open bracket. So I'm going to basically have 2 little segments for the domain. And when you have segments that you're going to join together, you do that with the union symbol. Open bracket means it's open. And it starts at 2. And it keeps going until the right-hand edge of the figure here at 4, which is a closed circle, so it's a closed bracket. So that's my domain. -2 to 0, closed brackets on both, unioned with 2 with an open bracket to 4 with a closed bracket. The range is going to be a little bit simpler. I start at the bottom, and I go up until I hit my figure, and I hit my figure at a y value of -2. And that's a closed circle, so it's going to be a closed bracket. And then I keep going. And notice that there's no gap here in the y's. There's an overlap. And that doesn't matter. That just means as I keep going, I'm going to have some y value somewhere. And the top of the figure looks like it's at a y value of 2. And it's a closed circle, so it's a closed bracket. So I have a range of -2 up to 2.
The last thing we're going to do in this section is find the domain of algebraic expressions or equations. And this is really a lot easier than most people make it out to be. You only have 3 problem areas to worry about in this course. The first one is when you have a variable in the denominator. And as hopefully you know, you can't have a 0 in the denominator, so all you have to do is make sure the denominator doesn't equal 0. The second problem you'll run into is radicals with an even index. That's square roots or fourth roots. If you have cube roots or fifth roots, this doesn't apply. Only applies to roots with an even index. But if we have even index roots, you can't have a negative under the radical. The third problem area you'll run into is logs, which will be at the end of the course, so don't worry about those yet. Right now you just have to worry about variables in the denominator or radicals. So when they ask you for the domain of something such as this, just ask yourself, do I have variables in the denominator? No, in this case we don't have a denominator. And do I have some radical? Nope. And if you answer no to both of those questions, the domain is all real numbers. So let's do one with a problem. Y equals 2 over 2x minus 1. And I want the domain of that. What you're going to do for this is take whatever's in the denominator and figure out where it's 0, which basically means solving for x. So bring the 1 over and change its sign when you cross the equal sign. Divide everything by 2, and I get x equals 1/2. So this denominator will be 0 at 1/2. So what I have to do is start with all real numbers and exclude 1/2. So how we exclude things is starting with all real numbers, write it like this. In other words, negative infinity goes up to 1/2. The open bracket means we're not including the 1/2. And I'm unioning it with this little interval. It starts almost at 1/2, but not quite, because remember that open bracket means I'm not including the 1/2, and goes up to infinity. So if we exclude points, we add that little bit of notation in. So that little 1/2 with the union sign and the other 1/2 means we're excluding the 1/2. Now let's try a slightly harder version of this. And you're going to be getting quite a bit of these, so you need to get used to factoring. First thing we're going to do when we see something like this is we know we have variables in the denominator, and I need to know where this equation in the denominator is 0. So the first thing I'm going to do for that is factor. And fortunately for us, this factors nicely. And then I'm going to set each of these factors equal to 0 individually, because if this factor is 0, it doesn't matter what this one is, the entire denominator is 0. And likewise for this one, if this one is 0, it doesn't matter what this one is, the entire denominator is 0. So let's just look at x minus 1 and see where that's 0. All I have to do is bring the 1 over. So this factor is going to be 0 when x equals 1, so I have to exclude the 1. And let's do the same thing for the x minus 2. Just bring the 2 over. So when x equals 2, this factor is 0 and the entire denominator is 0. So I have to exclude the 1 and the 2. So for the domain, I'm going to start at negative infinity, and we're going from smallest to largest, so I'll start with the 1, and I'll exclude that, and I know how to do that. I just add that in. And then I'm going along up to the 2, and I'm excluding the 2, and I know how to do that, and then I continue on to infinity. Now let's try finding the domain of a radical with an even index. And the problem here is that the radicand, or whatever is underneath the radical, can't be negative. So to solve this one, I'm going to take whatever's under the radical and set it greater than or equal to 0. And then I'm just going to solve this equation. So I'm going to bring the 3 over. And I'm going to divide both sides by 2. So I get x is greater than or equal to negative 3/2. Now all I have to do is write that in interval notation. So because it's greater than or equal to, it's close bracket, the negative 3/2, and it goes on to infinity. Let's try one more. Let's say that was a cube root. Okay, well, remember our two rules. Do we have variables in the denominator? No. And do we have a radical with an even index? Well, no, that's an odd index. So if we don't fall into one of those two problem areas, the domain is all real numbers, negative infinity to infinity. And that, at the moment, is really all there is to algebraically finding the domain of equations.